Okay, I've been talking to PaulGradenwitz. This is something that PaulGradenwitz said. He said that the observer at the edge of the plane of now, let's say this is the plane of now. He says that the observer at the edge of the plane of now, say right here, would not know what I meant by the plane of now. And so he would, of course, he would think that this was the plane of now, so that it would cross down here and there and to the spot where it crossed the plane here. This and this would be equidistant on this graph. Is the purple now, and this is the blue now. This guy is in the center of his own plane of simultaneity, and that plane, that is coming up. Boy, I've really screwed this thing up a lot, but that is his plane of, that is the center, we'll call that the blue here, and we'll go ahead and make a purple one too for the purple here. He's in the center of his own plane of simultaneity. If you take an event at a position in the plane now of the origin, but at x equals 0.99c, so like this one here, yeah, then a Hubble-flow observer over there has a level of simultaneity that is so inclined that it nearly intersects with the bottom of the world line of the origin observer. So yeah, down, way down there. He is of cause not interpreting himself at the edge, although he might find out from the stellar aberration that he is at the edge of the explosion. So that's kind of referring back to something I said earlier. If this explosion sort of ended with particles going out at 0.999c, then the guy here traveling at x equals 0.9c or 0.99c would find himself at near the edge of this explosion. But if this guy here is at 0.99c and the explosion is 0.99999999999c, then he's not going to be able to detect the edge of the explosion. Now, would he be observing a huge amount of light coming from the direction of movement? Well, remember, the direction of movement for all these particles is still away from him. He's not going to be, there's not going to be any asymmetry in that. So if the explosion was small, then there would be an asymmetry because you would notice more light coming from over in this region than over in that region. But if it's big enough, there's not going to be any noticeable difference. Let's see, his time is running much slower than the time for the observer at the origin, x equals 0. Okay, so this is dependent on something else. We have two sets of clocks to look at. We can go with the purple clocks. The purple clocks are going like this, and those purple clocks are Euclidean points in this space. So if I were the blue guy, let's draw that one more time, the here. I'm going to draw it in green now. Okay, so if I'm this green guy, whoops, I'm this green guy and I'm comparing my clock to the purple clock that's passing by, and it's going to, these are, because I'm going to be passing different different purple clocks. I'm going to be passing one here, passing another one here, passing another one here. And guess what? As I pass those clocks, you're right. Green here, his time is running much slower than the time on that adjacent clock. As he watches that clock go by, if he compares his clock to that clock time, his time is running much slower than that time. Not going to do that because those clocks don't actually exist. What he might do, where were we? 1, 2, 3. We were on, whoops, come on. What he's probably going to do is imagine a bunch of clocks that are running parallel to this line. And if we look at that's going to be x prime equals 0, x prime equals 1, x prime equals 2, x prime equals 3. And he's going to be looking at lines of simultaneity crossing like here and here and here. My slope isn't tight enough because you can see the tops of those triangles are about accurate. But when he does that, he's going to look back at the clock here, and he's going to say that clock is, if he just looks at this clock, this clock, he's going to say that clock is running really slow compared to mine. And these are inverses. So his time is running much faster than the time for the observer in the origin. And he can compare that. Of course he can compare that because he can actually see that observer at the origin. Of course, he's going to observe it on his past light cone, which is going to actually come down all the way down to here. So he's actually going to see that observer there as in its primordial state. He's not going to see anything except those early events in history. He only sees like the hydrogen formation or whatever, the surface of last scattering. All right, in this part of Paul's description, I would like to make two corrections. I feel like these could be, them is, I hope, is just a typo. I just need to cross out that word not. And the other issue, I kind of want to make a correction where he says the origin, the event should say the Euclidean point. Every Euclidean point did start moving through time. And really, there's no point in saying that it moving through time. It didn't really start. But yeah, we can come back to, if he's talking about a Euclidean point passing through time, for the observer at the origin, you could just say that these Euclidean points exist, and you could map them all the way back into history and say this is t equals 0. And say here, we'll call this, I don't know, here we'll say that's t equals 13.7 billion years. And if there is movement through space, then there is time dilation. For the observer at the origin at x equals 0, he will state that the universe is 13.7 billion years. And so he would put the universe at 13.7 billion years there at his level of simultaneity. Every Euclidean point started moving through time didn't really start moving at t equals 0. All the Euclidean points existed before then. And his level of simultaneity did start moving, so you can start drawing these parallel lines even before t equals 0. For an observer on the same plane of simultaneity now, but with speed v greater than 0. So I'm gonna go ahead and make that change and take away that not, because otherwise I don't think I can make this make sense. The time will run slower, so if you're here, then the time is running slower than here. So we look at this point, and actually let's even use a more drastic one, something way over here. Okay, so here's now for this guy. That guy is not going to reach that now until I should just go ahead and draw it there. So according to him, at this point, let's draw that one in a different color so that I can. So at this point, the universe is not going to be as old. When he experiences this event, the universe is not as old as this guy perceives it here. And also, his world line is going to point back to that point there. And he will assume that he is at x equals 0. Now, as far as it being related to rapidity, there is no difference in the view. The rapidity thing is just another way of expressing it. The rapidity is inverse hyperbolic tangent of v, and the rapidity view only does not change this view at all. There's no difference. Because the rapidity is just a simple function of the velocity. There's no, it just takes the numbers -c to c and maps them to a coordinate that goes infinity, -infinity to infinity. No difference other than that. The rapidity space does give a better sense of how these things are distributed, though, because it's very confusing, as you saw earlier. Or did we? Was I working on this video at the time? I talked about something being between 0.99c and 0.99999999c. Okay, it takes a lot less time to say something like v equals 1, rapidity equals 1 for this case, and v equals 10 for this case. It's not